Okay, hello. Okay, hello everyone. Today we are going to study the details introduced on lecture 7. Okay, here we go. I guess I got some technical issue now. Please wait 1 second. Let me see. Okay, yeah, it's working. Cool. So in this lecture, we are going to study the carrier scattering mechanism in great detail. Afterwards, we're going to develop the analytical equation for drift current. Then we are going to derive the equation to describe quantitatively the conductivity as well as resistivity. Then we're going to learn how to draw the band diagram to indicate the voltage difference as well as electric field intensity within a band diagram. Okay, so let's move forward. And the first step herein is mechanisms of carrier scattering. So as we have studied in the previous lecture note, there are three carrier scattering mechanisms. What are they? Number one, phonon scattering, right? What is the phonon? Yeah, vibrating silicon atoms itself, okay? And the second scattering mechanism is, what is that? Yeah, ionized impurity scattering. Okay, so once dopant atoms, impurity atoms are included into the pure silicon material, then we should worry about any scattering event coming caused by ionized impurity atoms. What is the last scattering mechanism? Yeah, electron to electron or hole to hole or electron to hole, hole to electron. So simply speaking, carrier to carrier scattering. Okay, but this carrier to carrier scattering would be dominant when the silicon material is heavily doped or degeneratedly doped. Okay, so herein we're gonna study some more details on phonon scattering first. So phonon scattering here. So mobility value governed and determined mainly by phonon scattering decreases when temperature increases. So as temperature increases, the phonon scattering mobility value would decrease. So herein the mobility, the symbol mu has been used to indicate mobility. So mu phonon is proportional to what? So many physicists, solid-state physicists has developed many detailed mechanisms to explain and understand the mobility value by phonon scattering. And here is the answer. So mu phonon, mobility by phonon is proportional to the how long the average scattering time is, and in this case, in which the scattering event is governed by phonon. So, the average, time between two collisions is long, then the mobility of electrons and holes caused by and governed by phonon becomes higher. So that's, following your intuition, you're going to simply understand this relation. Okay. And here, a new words, photon density, carrier thermal velocity, those two stuffs are popped up. So what are they? Phonon density, how dense the phonons are created in silicon material. So, with a higher phonon density, more the phonon scattering will be happened. So phonon density is proportional to basically to temperature. So with increasing temperature, the density of phonon increases. Okay, so herein you can see that the T has been replaced into the phonon density. And carrier thermal velocity. So as we have learned, the average thermal velocity, we can use, this. Did you remember this equation? 3 half times kT is equal to 1 over 2 times mn asterisk times thermal velocity square, right? Then if we can calculate something, then many coefficients are there and t. So thermal velocity is proportional to the square root of temperature. Okay, so plug in the t to the 1/2. Okay, then if you do some simple math, then you're gonna end up with phonon mobility by phonon is proportional to what? Temperature to the minus 3/2. Okay, so as temperature increases, the phonon scattering mobility is degraded. Okay. Okay, now let's move on to the next topic, impurity ion scattering. So now we are talking about ionized impurity scattering. Um, as I briefly mentioned before, while the electron or a hole, any charged particle is moving and it is faced with ionized dopant atom, in this case, ionized boron atom are existing there, well, definitely the ionized boron cannot become mobile. Why is that? Because this dopant atom is electrically activated, which means dopant atoms are fully bonded by four neighboring silicon atoms with the help of covalent bonds by sharing the electrons uh, in between two neighboring atoms. So once a boron atom is well electrically activated into the crystalline material, then it's going to be ionized so that charged particles such as electrons and holes are traveling, and once they are, getting closer and closer, so the trace and direction of a charged carrier such as electron holes are the direction will be varied. Okay, so this scattering event can be happened because of the ionized impurity atom. How about the donors, arsenide? You know, same, right? Whatever the charge is signed, the ionized impurity atom would affect the trace and direction or traveling, traveling way of the carriers. Okay, resulting in ionized impurity scattering. And one thing that we can find out from this movement and this dynamics is as follows. There is less change, not too much variation. Where? In the electron's direction of travel. Okay, so in this figure, the electron's direction of travel is significantly changed. But here in this sentence, there is less, smaller amount of variation can be found like that. When? Here is the condition. When the electron zips by the ion at a higher speed. So if the speed of this electron is very high, compare against the speed of this electron, say this is a low speed, then if the speed of this electron is low enough, then this electron's direction travel is significantly changed. However, very high, the electron, this guy, the electron with a very high speed uh, wouldn't be significantly affected by this ionized boron. When? When if this speed, the speed of this electron is high enough, then less change in the electron's direction of travel can be happened. Why is that? What is the main, physics to explain these two different events? Well, here's the answer. It can be found in this verb. The electron zips by the ion. What is zip? You have your own clothes, and there is a zipper, right? So when you close your jacket, what kind of sound you're going to hear? zip, right? Just pull this hand upward, then you're gonna hear zip. So electron is, moves at a very faster speed than we can say that the electron zips. Okay, so electron zips by the ion at a higher speed, then less amount of change in the electron's direction of travel can be happened. Okay, so this verb itself can well explain two different events. And then now the topic is what is the mobility caused by ionized impurity atom? This term is proportional to what? Okay, so here we can do some theoretical thinking. Okay, what if there are more boron atoms here and there? So I'm talking about heavily doped silicon versus lightly doped silicon. And now the electron in two different silicon samples, one of which is heavily doped one, the other of which is lightly doped one. Then how the electrons in each sample moved? Well, in a heavily doped silicon sample, it would be affected by many, many different dopant atoms. So it is hard to be accelerated. In other words, it would quite often, quite frequently changes the electron's direction of travel. So the higher the doping concentration is, the lower the mobility of the electrons and holes are caused by ionized impurity atom scattering. Okay. Then what about the velocity, thermal velocity? If the electron is moving at a faster speed and this electron is moving very slowly, then which electron would have a higher mobility? Yeah, as described here, if the electron zips at a higher by the ion at a higher speed, then its mobility is good. Okay, so the higher the thermal velocity is, the higher the mobility caused by impurity is. Okay, and now let's replace this term with the temperature. In the previous slide, the thermal velocity is proportional to the square root of T temperature. So now plug in this equation into here, then you're gonna end up with this. And now let's take a look at the term here and there. Mu mobility by ionized impurity scattering, is proportional what? Temperature. This is kind of a sort of a constant that you can determine, right? So here is a temperature. Aha. So as temperature increases, your mobility increases. But based on your intuition, as temperature increases, more, the degree of mobility, degree of being mobile would be hurted or negatively acted. So in your mind, maybe you are thinking of this trend line. If temperature increases, the mobility of electron hole would be degraded, but mobility impurity is proportional to the temperature increasing. Haha. Yeah, think about this guy. This mobility is governed by phonon. Okay. In previous slide, as we have learned, mu phonon is proportional to the t to the minus 3 over 2. So if I draw this curve in t versus mu plot, definitely as temperature increases, the mobility value is degraded. Yeah, this guy. So we can intuitively understand for a given silicon lattice structure, just simply speaking, silicon substrate, if you heat up the silicon substrate, electrons and holes in the silicon substrate can be better easily moved or hardly moved. Yeah, the temperature for the silicon substrate is increased a lot, then many silicon atoms consisting of the silicon substrate, many silicon atoms are vibrating too much. So it would cause significantly phonon scattering. Okay, so as temperature increases, the electrons and holes, those two carriers are very tough and hard to move forward. So in that sense, the degree of being mobile of each carrier has been hurted and degraded when the temperature increases. So all these things can be happened by phonon scattering. However, if that silicon substrate is heavily doped or lightly doped, anyhow, it is doped, then depending on the doping concentration, the mobility of electrons and holes caused by ionized impurity scattering would be determined. So with a higher doping concentration, your mobility value caused by ionized impurity scattering is degraded. So that makes sense. With a more, impurity atoms, your, electrons and hole cannot move very well. Okay. But here, one interesting point is if even though the silicon substrate is heavily doped, the temperature applied to the silicon substrate is increased a lot. Then definitely more phonon scattering will be happened. However, from the perspective of how mobile the electrons and holes are when the temperature increases, the electron and hole mobility is going to be increased. Why? The, because of the high temperature, the kinetic energy or activity or active electrons and holes will be created a lot. So those are very active, so their speed is very high. So the active electrons and holes can zip by the ion at a higher speed, as I told you before, so that in terms of mobility governed by ionized impurity, as temperature increases, its mobility is increasing. Okay, so whenever we are searching how how good the mobility of electrons and holes are, we should always take care of and watch out the temperature regime. Okay, so let's do this plot first. So here in the inset, you can see that mobility versus temperature. Okay, and you can see that this t to the minus 3 over 2 region and t to the plus 3 over 2 region. So those two regions are separated, and depending on the temperature, impurity scattering would be dominant or lattice scattering would be dominant. But in general, at a higher temperature region, the lattice scattering is way more dominant than the impurity scattering. At a lower temperature regime, impurity scattering is way more uh, higher than the lattice scattering event. Okay. Then the question is, what is kind of critical temperature to separate left side one and right side area? Okay. So in this data, so all the solid black colored line indicates the measured data. So when the silicon sample is heavily doped, 10 to the 18, the critical doping concentration to classify this silicon is degenerately doped or not. So there is some complicated, tricky number, but just ignore them, and you can think of 10. You can. I ask you to remember 10 to the 18 per cubic centimeter. That is a key and critical doping concentration to say this is heavily doped or this is lightly doped. Okay, so when the doping concentration is high enough, you can see that, especially in the case of 10 to the 19, you can especially see that around here maybe. Okay, uh, at room temperature, the mobility value is high. The highest mobility can be found at room temperature, near room temperature, when the silicon sample is heavily doped. And as temperature decreases, or I'd say as temperature increases from 200 Kelvin toward 300 Kelvin, the mobility increases. Why is that? Because of phonon scattering is nothing. It can be negligible. However, the impurity scattering is a main one. Okay, so as temperature increases, the mobility also increases. However, at a temperature higher than 300 Kelvin, okay, then as temperature increases, the mobility decreases together. Okay, why is that? Lattice scattering or phonon scattering is more dominant than the ionized impurity scattering. So uh, in a silicon sample with very heavily doped, in a silicon sample which is heavily doped, we can clearly see the two different trend line mu in the plot of mu versus t. However, at a lightly doped case, 10 to the 14, 10 to the 15, 16, 17, it is hard to see the uh, two separated region. Only one side, in this case, lattice scattering dominant area, right? So if we tried to measure more data, maybe at some point it's going to be it's going to be maximized and then slope over. Okay, so if I draw the top edge line, then it looks like this trend line. Okay, my pen is not working perfectly today. Anyhow, so this is the physics, physics of temperature impact on mobility in silicon material. Okay, then now let's go back to this slide. We have studied mu phonon and mu impurity. How to combine them? Can we simply sum those two values up? Is it physically reasonable? So to address this question, we're going to study Machisson's rule first. So Machisson's rule said the probability that a single carrier electron or hole will be scattered out by mechanism, say I, within a time period, very short time period, dt. So but it's hard to understand it. So I would say, suppose that this is 1 second. So for a single second, mechanism I is hard. Just say phonon. So because of phonon, within 1 second, a carrier can be scattered. What is the probability value of that? So at 1 second, I would say this is time. Okay, we can start at 0, 1, 2. For suppose that phonon scattering is happened every 2 seconds. Okay, so every 2 seconds, phonon scattering will be happened. So from 0 to 2 seconds, you're gonna see single one phonon scattering with 100% probability, because I said every 2 seconds phonon scattering is happened. Then the question is, what is the probability of a phonon scattering is happened within a second, within 1 second? Well, if we wait for 2 seconds, we're gonna see a single phonon scattering event, but we should wait for 1 second. Then with the probability of 50%, we're gonna see the phonon scattering event. Then let's do this. Every 2 seconds, phonon scattering is happened. Okay, so every 2 seconds. So here, tau sub I, take a look at tau sub I indicates what? The mean time, average time between scattering events. So previously I said from 0 to 2 seconds, one scattering has happened, and 2 seconds later, the other event, scattering event has been happened. So in between, every 2 seconds, I said phonon scattering is happened with 100% probability, which means the mean time, tau sub, I said a phonon instead of I used the phonon, is 2 seconds. Okay, But the time window that I'm looking for is from 0 to 1. Okay, so I said we have reached to the conclusion that in a 1 second time window, we're gonna see the phonon sketching with a probability of 50%. So to derive the number 50%, let's do this. So every 2 seconds, but every 2 seconds a single phonon sketching is happened. But the time window that I'm looking at is 1 second. Okay, so this is quite well matched to this guy. Within a time period, very small, tiny, short time period dt, and the average, mean time between two collision is tau sub I. So this concept has been well smeared and explained in this equation. Okay, so whatever the mechanism I is, this within a very tiny time, very short time period, and once we know the average time between two scattering events with 100% probability, then we can simply estimate this probability for any time window, say here, here, here. Any time window, we can mathematically estimate the probability value. Okay, so herein the probability that a carrier will be scattered within a time period dt is described as a dt over tau sub I. But here you can see that sigma, what is this indicating? Just sum them up, right? Just sum up. So I said a mechanism I, but in silicon material, we're gonna have two mechanisms. What is this? Phonon scattering and impurity, ionized impurity scattering. So that we're gonna have two different scattering events, scattering mechanisms. So uh, let's do this. Different color, please. Okay. Every 3 seconds, one impurity scattering can be happened. So if we wait for 3 seconds, with 100% probability, you're gonna see the single impurity scattering. And now the time window is still 0 to 1. Then in this within a 1 second time period, do you believe you can see a phonon scattering as well as impurity scattering together? If so, what is the probability value? Okay, so to estimate the probability value for the time window of 0 to 1 second, let's use this guy. In this time window from 0 to 1 second, we're gonna expect two different scattering mechanism, one of which is phonon, the other of which is impurity scattering. So we can separate them. Okay, so in this 1 second time window, phonon scattering is happened, and phonon scattering maybe happened. So let's estimate the probability value of finding phonon scattering event. How to do that? Yeah, let's use this guy again. So every 2 seconds, but the time window that I'm looking at is 1 second. So 1/2, 50% probability value, which is for what? Which is for phonon scattering. Okay, so this guy is phonon, but that indicates a probability value. Okay, probability value of finding phonon scattering event in a in a one in a time slot between 0 to 1 second. Okay, but uh, I asked you, I I have assumed that there is another mechanisms to be happened in this time window. What is this? Ionized impurity scattering. But in this case, the mean time, average time between two scattering events is 3 seconds, not 2 seconds in this case. So 3 seconds, and the time window that I'm looking at is still same, right? From 0 to 1 second, so 1/3. So with the probability of 33%, we can see and we can expect the ionized impurity scattering in the time window between 0 to 1 second. So now we estimated two different probability value that is caused by impurity scattering probability. That is probability. So for the limited time slot from 0 to 1 second, we have obtained the two different probability values. One is mainly caused by phonon scattering, the other one is mainly caused by impurity scattering. Then the question is, in this time window, uh, it doesn't matter the type of scattering mechanisms. The question is, what is the value, probability value to see any type of scattering event? Then, well, he asked me the probability value of scattering events. Well, in this case, a scattering type doesn't matter. Then you can simply sum two probability values. Then you're gonna see the total probability values. Okay, so 1 over 2 plus 1 over 3 is the answer. What is it? Yeah, 5 over 6. Okay, so the probability of 5 over 6, we can see and we can expect a single scattering event to be happened in the time interval between 0 to 1 second. Okay, so this equation would be valid. So now the question is, 1 over tau means, the average scattering time between two scattering events by any mechanisms is equal to what? 1 over every mean time between two scattering events only by phonon scattering plus, well, this guy indicates a probability. Okay, like, well, this one is identical matched to the time window from 0 to 1. 1 second, you may think of it one as a 1 second time interval, but in your textbook maybe it is described as dt. dt indicates the time interval that you are looking at, but just to make your life easier, I used 1 second as dt. Okay, even though you're going to use a dt, you can cancel those three dt's, and it's going to be end up with 1 over tau is equal to 1 over tau phonon plus 1 over tau impurity. Okay, we're almost done. Well, final destination that we are going is mobility. Okay, so going back to the definition for mobility, what was the definition of the mobility? Did you remember this? Drift velocity is proportional to the electric field intensity. And what is the coefficient for this? Yeah, mobility. So Vd is equal to mu times E. And how to define the mobility? Did you remember this guy? Momentum is conserved, right? And F times force times time. So this time indicates you know, average or mean time between two scattering events. And F indicates, uh, m and asterisk times acceleration times tau. So from this derivation, we're going to end up with mobility can be defined as small q unit charge times scattering time between two different scattering events and divided by effective mass. Okay, so now mu, and here is tau, this tau. Okay, and q is a unit charge, and mn asterisk indicates the effective mass. So tau is equal to q mn asterisk times mobility. So plug in here, then this mn asterisk over q is a common term for all these terms, so they are going to be canceled out. So in the end, instead of tau, you can just place a mobility mu. That's it. So we're gonna end up with this equation. Then now we can add them up. We found the mu phonon and mu impurity. then what is mu total? Can we simply add them up? No. The answer can be found here. The total mobility can be defined by uh, this equation. Okay, so please remember this equation, and that equation is derived from the Mathison's rule. Okay, all right. Following the Mathison's rule, and many experimentalists has done many works to investigate the mobility value of electrons and holes as a function of doping concentration in silicon material. So in silicon substrate, if your doping concentration is say 10 to the 17, just simply by reading out the value from this plot, you can say that the hole mobility is something and electron mobility is something. But herein, watch out that the doping concentration is Na plus Nd. Suppose that this silicon sample, say that could be your, your transistor MOSFETs, this silicon sample would be your source side of the MOSFET. This is gate and drain. Okay, this is oxidation layer. So this source is very heavily doped, say 10 to the 20, as N plus. Drain is N plus, body is P. But here question is, this source region has been formed in the P-type substrate. Okay, so originally this area source region has been formed at has included tons of acceptors. However, the number of donors is more than the number of acceptors in this source region. So even though we are saying that this is N plus silicon sample, so that is very heavily doped N-type material, so that would be governed by ND. But there is acceptors concentration, but if you calculate the net doping concentration, since ND is much higher than Na, so this is simply N sub D because ND is much higher than Na, so you can ignore these two guys. So simply speaking, in N-type silicon material, the total electron concentration equal to the N sub D. Well, definitely you should take out the Na, but this number is much smaller than Nd, so simply N is equal to Nd. However, in this slide, take a look at here. You should consider acceptors and donors together when you are estimating and when you are reading out the mobility value of each carrier. Why is that? Why don't you use simply Na minus Nd or Nd minus Na? Instead of using total doping concentration, can we use a net doping concentration on x-axis? Is it possible? Does it make sense? In some sense, it sounds reasonable. But how come previous original researchers has used the total doping concentration for x-axis? Why is that? Go back to this slide. Boron versus arsenide. We're going to have two different types of impurity atoms together in a certain region, such as source drain region of MOSFET, NMOS in P substrate. Okay, so always when it comes to the scattering mechanism, we are always thinking of two different types of impurity atoms, borons, acceptors and donors. Okay, and those two guys, acceptor donors, would significantly affect the electron's direction of travel. You don't need to cancel out, the arsenide ion because the total number of arsenide ion is smaller than the total number of boron ion. You don't need to ignore. You should not ignore the dopant atom, the total number of which is smaller than the others. It is not allowed, at least when it comes to estimating mobility value. Okay, so going back to this plot, if your job is to look for the mobility value for electrons and holes. Always think of and always try to look for the right doping concentration value. In this case, you should use total doping concentration, not net doping concentration. Okay, so that's a key message here. And I'm going to stop here because the quite different topic will be explained from this slide. So I guess I would like you have a short break time, and please review what you have, review all the materials that I has taught, and go back to your textbook and read the sentences in chapter 3, the early chapters, the point 3.1, I guess, chapter 3.1, that would be corresponding to the mobility stuff. So please have your own time to review all the materials regarding the mobility. Okay, in the next movie clip, I'm going to begin with drift current. So we're gonna develop the analytical equation to analytical equation for drift current. So the answer can be found here. Q times P times VD, drift velocity, hole concentration, unit charge, will give us the current density. Okay, so we're gonna do derivation work for the to obtain this final, final shape or final form of analytical equation for drift current. Okay, so if you have some time, please preview all the materials afterwards. Please take my recorded lecture. Okay, all right. Thank you very much. Thank you for your attention, and see you in the next movie clip. One official announcement is if you have any question, please join my WebEx meeting room every Tuesday, 3 p.m. TA and I will be there to help and address your questions. Okay, thanks for your attention. Bye bye.